Hello everyone. Welcome to the SWAM NPTEL course on Mathematical Geophysics. We continue with the Module 4 Mathematical Modeling Part 2. This is the fourth lecture, Electric Potential. In this lecture, the concepts covered are electric potential and various applications and derivations of the electric potential. The basic concept of electric potential is covered first. This is followed by Poisson's and Laplace's equation. Next, we consider electric field outside a solid sphere. Next, we have the electrical potential inside and outside a spherical shell. We will be looking into both the field and potentials. Next, we have boundary condition on electric field and the boundary condition on electric potential. So, let us begin. First, the electric potential. We have discussed in previous lecture that the electric field is a conservative field. This is because the curl of the electric field is equals to 0, having been obtained from the Stokes theorem applied on the circulation. This gives the line integral of E around any closed loop equals to 0. Thus, we can have a potential function for this field. This potential function is called the electric potential. The electric potential relative to a reference point is V r vector given as minus integral E dot dl. Now, this is with respect to the point O, such that Vr is the work done by an unit charge at O to reach the location R. We can obtain the mathematical representation of this potential function. Let us look into the electric potential as the difference between 2 points A and B. If A and B are as shown here with the location reference as O, we can have the electric potential at B and A given by this expression where the R is substituted by B and A respectively. The integral from 0 to A plus the integral from 0 to B. This results in integral of E dot dl with minus sign instead of plus sign by reversing the integral exponents. Now, by combining this, we obtain Vb minus Va equals minus integral A to B of E dot dl. This is nothing but the circulation from A to B, or the line integral of E along any path joining A to B. Since this is a conservative field, the path is not a factor. As E can be written as gradient of V, where V is the potential, we can have integral A to B grad V dot dl equals integral E dot dl. This is possible as E is a conservative field which can have a potential function, and E can be written as the gradient of the scalar potential V. Now, using this potential function formulation, we can look into the equations that govern the potential function V. First, we will use the Gauss law. The Gauss law for electric field states that the divergence of the electric field equals rho by epsilon naught. Replacing E by minus gradient of the potential function V, we can obtain Laplacian of V equals rho by epsilon naught. This follows from the vector identity, that is divergence of a gradient of any scalar function V equals Laplacian of that scalar function. This is the Poisson's equation. In the case where there is no charge, that is rho equal to 0, the Poisson's equation becomes the Laplace's equation. Next, we look into the electric field which is outside a solid sphere which is having a charge distribution. Now, this solid sphere is considered to be having a uniformly charged distribution. The sphere has a radius r. The dark gray circle represents the sphere with radius r. Now, the total charge distribution on the surface is equal to q. To measure the electric field outside such a uniformly charged sphere of radius r is the aim of the next exercise. For that, let us consider another hypothetical concentric spherical surface located at a distance little r which is greater than capital R. This sphere is colored lighter gray. Now, at any point on this sphere, we can have the outward vector ds vector representing the elemental surface area ds. We also have the electric field along this ds vector. Now, Gauss' law states that electrical field dotted with ds and integrated over the entire surface area is equal to the enclosed charge by epsilon naught. In this case, the enclosed charge equals q. We also use the symmetric property of the sphere. At any point on the sphere, the electric field is going to be same because such points are all equidistant from the sphere which is charged. Thus, we can conclude that the electric field can have a similar magnitude for all these points. The difference is that the ds vector points in different directions at each of these points. Thus, the integral E dot ds simplifies to E vector modulus, which is the magnitude, and integral ds. This equals q by epsilon, where q is substituted in place of the q enclosed. The surface area of the sphere is 4 pi r square. This is the integral of ds. Now, substituting that, we have E equals q by 4 pi epsilon naught 1 by r square. This is the magnitude of the electric field. The direction of the electric field is always outward in the radial direction. That is the direction of electric field at any point on the surface of the sphere. Next, we consider the electric potential inside and outside a spherical shell. This diagram shows a spherical shell of radius capital R. The point P is the test point which is located outside the spherical shell. Now, this point P is at a distance little r from the center of the spherical shell. Now, little r is greater than capital R for the case where P is outside the spherical shell. This case is considered first. The electric field is given by Q by 4 pi epsilon 1 by R square. This is because the electric field expression has been obtained for a charge distribution as E equals 1 by 4 pi epsilon integral dq by R square. This integral dq becomes equals to q for this case. This means that the total charge distribution on the sphere is equals to q. Now, the potential for the points outside the sphere is the work done by the charges to take a unit charge from the reference point O to R. Thus, VR equals minus O to R E dot dl, which is equals to 1 by 4 pi epsilon integral infinity to R q by R square dr. This gives 1 by 4 pi epsilon q by R. The reference point is chosen at infinity. Thus, the potential is essentially bringing a point charge from infinity to R. The field inside the shell is now considered. Since inside the shell the field is equal to 0, we can derive the potential for points inside the sphere as VR equals minus infinity to R E dot dl. Now this equals minus 1 by 4 pi epsilon integral infinity to R q by R square dr minus integral R to R 0. This comes from the absence of any charge inside the spherical shell. This gives the VR equals minus 1 by 4 pi epsilon naught integral R to R q by R square dr. Remember that R is less than capital R for a point like this. Thus, we have the final expression for the potential as 1 by 4 pi epsilon naught q by capital R. Now this is a constant quantity as long as the q remains same. Thus, we can say that the potential for all the points inside the sphere is constant. There is no potential difference inside the spherical surface. This indicates that the gradient of the potential inside this spherical surface is equals to 0. This is same as the field being 0 inside the shell. Thus, we reinforce the idea about the absence of a field and hence a constant potential which are equivalent from the case of the field inside a spherical shell. Next, we will discuss the boundary conditions on electric field. The boundary conditions on electric field refers to the conditions that may be imposed on the boundary which encloses the region where electric field exists. For example, let us consider a thin sheet which extends over the edges in both directions. This is shown in this diagram. Sigma is the charge density. We have the surfaces which are above this thin sheet and the surface which is below this thin sheet. Thus, this thin sheet acts as a boundary between the above space and the space which lies below this thin sheet. Consider an area A on this thin sheet. The charge density, which is the surface charge density sigma, is uniformly distributed on the surface of the sheet. Thus, the Gauss law gives integral of E dot ds, which is nothing but the flux of the electric field, equals Q enclosed by epsilon naught, that is equals to sigma s by epsilon naught. Sigma s is the total charge. Now we will look into the boundary condition in two directions. First is the normal component, second is the tangential component. The normal components are directed along this direction, which is perpendicular to the thin sheet. The sides of the thin sheet contribute nothing to the flux because the sheet is extremely thin with epsilon, that is the thickness of the sheet, going to 0. We have the electric fields above and below forming the flux. This is because the electric field above and below is the difference in the flux which is crossing through this thin sheet. From Gauss law, this difference can be equal to sigma by epsilon naught. This also comes because integral ds equals s. One can write integral ds as the difference multiplied by s. Upon equating this to this expression, upon substituting this into this expression, we have this expression where the difference in the electric field above and below this thin sheet equals sigma by epsilon. This implies that the normal component of the electric field is discontinuous across a thin sheet carrying a charge density sigma. This discontinuity is by an amount sigma by epsilon naught at the boundary. Next, we consider the tangential components. We will consider the line integral of the electric field to the rectangle loop as shown here. This is the same thin sheet with charge density sigma. Here we are considering a rectangular loop which goes above and below the thin sheet. This rectangular area is having a length L and a thickness which is slightly more than the thin sheet, such that the rectangle moves in above the thin sheet and below the thin sheet. If we consider the integral E dot dl across this entire loop of the rectangle, it goes to 0 because this loop has the arms in space above and below the thin sheet where the charges are not existing. Remember that the charges only are located on the surface of the thin sheet. The sides of this loop do not contribute to this integral in the limit epsilon tending to 0. Thus, the tangential components indicated by this parallel superscript is obtained as E parallel above into L minus E parallel below into L equals 0. This gives a better understanding where the loop is enclosing the thin sheet having a charge distribution sigma. These regions are taken into account for the integral, but they do not contain any charges. Hence, E parallel minus E parallel above and below into L goes to 0. Thus, we have our boundary condition for the tangential component, which gives that the tangential component of the electric field is always continuous across any surface having a charge distribution sigma. Thus, the total boundary conditions on an electric field is E vector above minus E vector below equals sigma by epsilon n cap. Here n cap is the unit vector normal to the surface. Since the tangential component is absent, the resultant boundary condition is directed along the normal to the surface area. This gives the overall idea of the behavior of electric field on boundaries. Next, we consider the corresponding boundary conditions for electric potential. We have the same thin sheet with charge distribution sigma. We consider 2 points A and B which are located slightly above and below the thin sheet. The potential distribution is such that the difference of potential between these 2 points, that is V above minus V below, can be given as minus integral of A to B E dot dl. This is nothing but the circulation of the electric field from A to B, because the potential difference is such that the potential is the work done from bringing a charge from infinity to point A. Hence, the difference is just taking the charge from A to B, which is nothing but E dot dl integrated from A to B. Now, for thin sheets, epsilon goes to 0. That means the length or the distance of separation between A to B shrinks to 0. Thus, A and B become a coincident point, which makes the potential equal. Thus, the boundary condition for the electric potential implies that the potential is continuous across any boundary. Even if the boundary has charge distribution of density sigma. Now we consider both boundary conditions on electric field and the electric potential. Electric field boundary condition and electric potential boundary condition, when combined, can give the potential gradient difference equals minus sigma by epsilon naught. This is obtained just by substituting minus gradient of V in place of E. This is written as normal derivatives of the potential above and normal derivative of the potential below. The difference equals minus sigma by epsilon naught. In other words, the gradient of V is discontinuous across the boundary. Thus, we can conclude that the electric potential, which results from the conservative property of the electric field, can be widely used in geophysical applications. The geophysical applications which use electric potential for their understanding and interpretation are locating groundwater, mineral deposits, hydrocarbons, and geothermal reservoirs. The electric potential also is instrumental in techniques like magnetotellurics, which explore shallow depths to deep crustal structures. Essentially, the potential of the electric field, which is induced due to artificial methods in geophysical systems to understand subsurface properties. The mapping is obtained from distortion of this potential due to the presence of anomalous bodies having different material properties which are electrically in nature from the surrounding. Thus, electric potential can be used for various geophysical applications which depend on subsurface bodies having anomalous changes in the electrical properties from the surroundings. One can refer to the following references for more details on electric field, electric potential, and other applications in geophysics. Thank you.